record it. Record the screen, and also let's check my presentation. All right. So I think you guys we talked about some hybrid process, right? Like the one we mentioned last time. That is the ultrasonic consolidation. I mean, so basically, this kind of process, the concept is it is the combination of the additive and subtractive manufacturing process. So like this one, basically the rough shape, the global shape will be generated using this ultrasonic consolidation. And then the fine tuning, the surface detail, the fine feature will be done by using the subtractive manufacturing. So, and there's some advantage and disadvantage for this kind of process. Let me check whether it is correct slides or not. Yeah, I think so. Yeah, it's over here. Yeah, because we have a similar slide, so I used to play the one previously. But okay, this is the right one. So as you can see, it consists of two processes. One is this ultrasonic consolidation, and then a milling process. And a similar thing happens to another metal printing process. That is the combination of direct laser deposition plus milling, right? And as you can see, the rough shape is generated using the laser deposition, right? And then the milling tool head will be applied to the rough shape to have finer surface finishing, like the one shown here. And the difficulty or the challenge for this kind of process, this combination, hybrid process, is what you also suggested in last class is the alignment of the two processes, right? How you make sure that the two processes will work together without some error introduced because of the alignment, right? That's one concern. Another one is you have to justify by using two different processes, you can gain more than what you have to pay, right? So the application is also very important because without the context, without the application of the process, it's very difficult to justify whether you should do it in this way or not, right? And that is another thing. When you choose a process, you need to consider about. So similarly, the wire arc additive manufacturing, the WAM process, also involves two different processes. One is this WAM additive process. Another one is this milling, right? So these two welding robots will generate the rough shape. And then a milling machine will be there for fine tune the final shape, right? Similar concept, but this one has the potential to build a larger part because basically this robot has better capability to access a larger space, right? And it's still under development, and there are a lot of challenges in both process and also the computational side, such as those motion planning, right? How you plan your motion such that you could successfully print the part you are expecting without any collision. Also, the efficiency has to be high, right? Otherwise, there's no point to doing this way, right? And again, it's context dependent process or application dependent. Again, you need to justify why in this scenario using this is a good choice. Some similar thing like this. That actually, I always talk about this point, not only during the lecture time, but also for your project. I always let you to criticize a scenario when additive manufacturing come in, right? Why it is a good choice here, and why it is a must requirement for additive manufacturing, so on and so forth. So similar thing to those hybrid process. Say, and just wait a minute, someone's knocking. Sorry about that. All right. Okay, sorry about this. So another possible combination here is the additive manufacturing plus the fused deposition modeling based. No, I mean fused deposition based additive manufacturing plus those subtractive ones, right? As you can see the figure showing here, first the part is printed using fused deposition modeling, and then a milling tool head will be applied to fine-tune the part. But as I mentioned in last class, basically it's quite doubtful that here is the right scenario for the two combinations. I mean, for the two combined together, because as you can see, it's quite messy, and all those materials will be everywhere around, and also the surface finishing, I would say, I couldn't see it's improved a lot, right? And I mean, to me, I'd rather to find other ways to improve the quality of FDM than apply this process. And again, in this scenario, it's hard to justify what you lost. I mean, what you gain is more than what you lost, right? So in this case, it's really difficult to justify this point. And well, it could be I mean, this process could be a good kind of exploration for the possible variations of different additive manufacturing process. But again, it's context dependent. Whether this process could be a successful way for combining the two, or it's just some random effort. I don't know. Yeah, the time will tell us. All right. And so right. So actually, there are some other additive manufacturing process. So the their direction is kind of changed the way that additive manufacturing is performed in a layer by layer manner. So this kind of process is called the layerless additive manufacturing. And the concept is to avoid or reduce the layer. So as you can see, for kind of a truss shape like this, right? So you can for this truss bar, right? That like this. If we manufacture it using the conventional layered additive manufacturing, basically it will the deposition position could be in this vertical direction, and you can see this shape could be accumulated by depositing each layer to each other. So that is the concept of current layered additive manufacturing. But what if? Because this is a bar shape, right? So one-dimensional shape. So what if instead of generate it in this direction, how about we use some extruding-based process and just along this direction? So as shown in this figure, basically the extruding head will move along this direction and a single bar will be extruded in this way. And by doing this, it avoids the layer by layer building method. So it's a layerless additive manufacturing. So how we kind of realize such kind of process? One possible implementation is to introducing the fiber optical cable like this, right? And basically, a certain pattern could be applied to this optical fiber. And if you have a stereolithography-based film resin like this, right? So you can easily cure the shape by projecting the pattern through this optical fiber to this resin. As you can see, you could generate this kind of curved shape without doing the layer by layer process. And also the orientation of this tool head could be adjusted according to your geometry. So it's quite suitable to generate those kind of single bar shape or those long protruded shape. So that's the concept for this process. It utilizes the optical fiber. It utilizes the fused deposition modeling. So it's combination of it's not fused deposition model. It's a stereolithography, SLA. So it's kind of a variation of stereolithography plus some new projection method, other than just those planar layers and in one direction. Because of the flexibility of the optical fiber, the projecting direction could be adjusted accordingly. Plus, the target object is some protruded shape or those bar shape, right? So that's the consideration for introducing the optical fiber to this process. All right. Okay, let's check more details for the hardware implementation. As you can see, the optical fiber is here, right? And also those circuits will control the projection and other and the motion of this extruding head. And the resin is here, right? It's similar to the original original SLA process. And to realize the adjustment of the motion, so you can see there are a different degree freedom such that this resin could move in not only XY direction, but also some motion will be applied to this extruding head, such that you could adjust the head as well during the extrusion process. So similar thing to this, similar thing to SLA. And but what can you make? For example, some shape like this. So as you can see, these are all long protruded shape. Rather than just build them layer by layer, you could extrude it just along the medium axis of this kind of protruded shapes. So it will give you totally different properties for the material. And also if the alignment is bad, I mean, carefully performed, you could have a better surface finishing. But I mean, of course, for this example, you couldn't tell what's the differences. But for some, if the size of the feature is smaller, and also if the alignment of the motion is performed correctly, then you will have much more accurate result. And I will show you. Let me show you some more results by looking at a website. Let me show you, because I realized what I show you in the slides is not such a good example. Let me show you something which you will know what will be a better application for this. Let me show you. I will find it on the all right. Okay, let me share the screen to you. So as you can see here, so basically, this is actually this process is developed by the Professor Yung Chen and his group at University of Southern California. And so basically, this paper you are looking at is a new method to generate those structural material, mimicking those bio structures. And it's very small features, and it's protruded features. Actually, this feature is kind of generated by using what I described, the optical fiber-based SLA process. And as you can see through this figure, they learned from the nature. So they mimic the structure in a flower and use it to some structural material area, and they kind of print this kind of structure to the material in a very small scale, such that the material could have much better mechanical properties than the previous structural material. But to actually fabricate this, they utilize the the optical fiber-based SLA process, which is what I just described in the lectures, in the slides. All right. Okay, let's move on. Actually, I would like to ask you guys to think about what could be the benefit for this kind of process. Any thoughts on this? So basically, you can check this illustration figures and think about some possible applications. All right, and you can share it using in the chat channel what we have. Anything in your mind? Yes, Doc. Yes. It for those protruded shape. If you just imagine, if you have a horn, right? If you print in one direction, I mean, probably at some point you need support to support it. But if you extrude it just along the shape, then yeah, that definitely eliminates the requirement for the support, right? So Michael's point is customer toys. So what kind of toys in your mind? Again, why this could be a good choice for some toys? I need some more details thoughts on that? What kind of toys, right? Any thoughts? I would say this is or you invent your own action figures. But what's the benefit to utilize this, to use this than others? That's it becomes my signature question when you talk about some application with some process. I always ask you why why choose this? Does not have rough edge. Yeah, yeah. So you mentioned the surface finishing for some of the shape, right? If you print it in this direction without the layer, then the step effect will be avoided, will be eliminated, such that you will have better surface finishing. I think that's a good point. Yeah. Any other thoughts? Okay, dogs. So you don't have to use the breaker bar or membrane to separate the cured PLA from the base. So can be completely submerged and not have to move the plate up and down. That reduce the number of moving parts. Yeah, yeah, that's true. Yeah, that's true. So basically, this kind of process, again, it introduces more degree freedoms because this printing head can move, can be adjusted in terms of the printing direction, right? So that will eliminate that. Also, it reduce the requirement of the separation force between layers. And but I think after all, this kind of process still has some I would say best fitting applications, best fitted applications. That will be printing object with very long protrusions, right? With curved protrusions. But for those shape with larger cross sections, with more regular cross sections, I don't think this will be a good choice. That's why they didn't extend this to a general additive manufacturing scenario. Instead, they utilize this to generate those kind of, as I mentioned, protruded features, right? Yep. All right, let's move on though. Oh, other suggestions. Let me check. Oh, Kristen, could you apply another degree freedom with this system? Good question. But but to answer this question, I have two questions to ask. Since okay, let me check what Kristen's follow up. Since this does not have to compete with gravity, what do you mean does not compete with gravity? I mean, oh, let's move back to the slide. So what do you mean it does not compete with gravity though? Oh, okay, okay, okay. I got your point. Yeah, yeah, you are right. So the printing head will move, will rotate, will has the capability to rotate, and that definitely eliminates some support material during the printing process. But you mentioned apply another degree freedom. So what's that? What's the degree freedom you mentioned here? Because we have XY, right? You can see on the platform, right? On the platform, we have XY, and this one also has a certain degree freedom to rotate this printing head. So what is the another one you mentioned. By rotating. Oh, okay. Yeah, yeah. So you mean because by printing on the, yeah, I think that could be but if you print against the direction of this resin tank, that could be problems because for some like you suggested, if you print downwards, there could be some collision between the tank and the printing head, and that makes things complicated. But it's definitely possible to add that one. But still, we need to think about by doing so, what can we gain by introducing this complexity or degree freedom here, right? So it really depends on what kind of shape you want to print. But for the paper I showed you, they are kind of printing those extruded shape in one direction. So this is perfect for their applications. All right. So that's this layerless SLA process. All right. And so another similar, I would say similar work, but with metal and a robot, is this MX3D, robotic 3D printer. And as you can see, those long protruded metal wires can be printed using this printing robot. Okay, let me show you this website. Oh, okay. Let me first find where it is, all right? And then show you guys. Okay, let me show you their video for this robot to print some large object. All right. Okay. All right. So another example is, let me show you. It printed a bridge in Amsterdam. Basically, this company is a Dutch based company. So you can see this video, right? Can you see this video? MX3D
Yes.
bridge. Okay. What?
Okay. Speed.
At first, they were little worm-like blobs. It was hard to see, but we saw a universe of possibilities. Of course, many things went wrong. A welding machine exploded, nozzles got stuck, and the robot got disoriented. But then, they became long lines, complex curves, and double-curved oval tubes. It was like drawing in midair. And after endless testing, we were able to speed up the process and produce this complex sculpture of lines. And now, we are ready for the ultimate poster project, to test all facets of this highly promising printing technology. A large-scale object that is functional and meaningful. We are going to print the steel bridge in Amsterdam.
All right. I would say this kind of although this kind of process, this work is quite interesting, but there are, I mean, some obvious limitations, right? So first of all, they use those wire-like structure, right? So that limit the capability for this work to be applied. Also, how strong it is, right? For many of the applications, this kind of structure just cannot stay long enough for the applications. Right? So Michael's point. So are they going to do an actual bridge, or pretty well known? Or was just the bridge the guy was walking across? Well, I don't think they are working on an actual bridge. They just kind of advertising their technology by showing some future possibilities. And I didn't see they built the actual bridge. All right. So Clay's point. Am I correct to think the material property are pretty well known? Because it's, yeah, exactly. That is the welding robot, but they managed to let the robot to print actually steel wires, right, to form some wire structure. But I think it will inherit all the advantage and disadvantage from the welding process. Yeah, I think one selling point is it can use the steel instead of other expensive alloy. That's a good point. But well, again, the shape of the structure is wires. So I'm quite concerned about how strong the object could be by using this robot printer to generate. And that really limits this technology in many of the scenarios. And also, like Michael pointed out, it seems they are still in the selling idea stage and haven't going to the actual real world application stage, right? So they can claim big, but what they achieved is relatively small. It's not there yet. Actually, I have some interesting conversation with one of the chief scientists of this company, because it's a Dutch company, And my PhD advisor is at TU Delft in Netherlands. And through him, we built little connection with this company. And we're thinking about to use this, build some like sculptures. So for sculptures, the shape will be the most important factor to think about, not the structurality, not how long it can stand there, right? So, well, some very weird shaped sculpture could be built using this, right? Okay. So is this Drew? Is Van? Who's Van? Okay. To me, that looks like flux core wire instead of gas shielded. Oh, Scott. Okay, sorry about it. So that may affect material property. Yeah, yeah, exactly. Basically, what can you imagine of the properties for welding? You can still. I mean, these properties will still work here in this scenario. And yeah, I would think it's the same thing. If the welding has this drawback, then this process will have the same thing. The dog's point. Seems public artists would love this. Yeah, that is what we are thinking about. So that's why we have this conversation with this company, because for those those modern artists, modern art practitioners, they have some really crazy design, and they utilize those wires, those truss a lot, and this could be their could be the way to build this. And yep, Kristen's point. How does it control layer thickness with respect to the bends and twists? I think it is. What do you mean? Oh, layer thickness. So the layer thickness here is kind of how much you extrude, right? If the slice, no, it's not SY. So that's the point, actually. It's not the planar slice, because you're following the path of the wire. So if you do the this XY, I mean the planar one direction slicing, you can never plan this motion. So again, this one and also the previous one, optical fiber-based SLA, they all do the slicing along the line. So that means you will have, I would assume the cross section is a circle. So basically you are extruding a small section of cylinder onto the existing one, right? So that will be another difference between this kind of process versus the conventional printing. So it utilizes a different slicing, as you guys did, Preston, right? So for this kind of thing, for this kind of process, you can never use the conventional XY slicing. That will definitely give you very bad result, because the surface finishing is already not good. So if you introduce additional error due to the slicing, you won't have a correct printed part by doing so. So the slicing will be done along the curve. Remember this. All right. Have you seen the MIT robot that uses expensive? I'm not sure which one you mentioned. So you can send the link to here, and we can take a look, and I can share to you guys. So that makes me think that this move away from slicing and more into standard. Exactly. That's the welding problem. It's not a. I mean, it's. I mean, the only thing here is related to additive is it. Well, even welding is adding material, so it's. I would say it's quite similar to welding. Almost a welding process. Yeah. Hi, Robert. Can you share the link if you have it? If not, we can talk about talk. Oh, yeah. Okay, I will share this link to everybody. Okay, good. Oh, I know this one. This is Oxmans, Nikki Oxmans. Um, she's a professor um, at MIT, and I used to attend her presentation last year. Yeah, yeah, I know this one. It's a yeah, it's quite a impressive. Yeah, it's a huge robot and built um, a big size object. Yeah, yeah, I know this. Yeah. Okay. Yeah, I think this work is pretty cool, and the point here is you can see the way a good work should. I mean, I would say the characteristic of a good work should be right. So basically, you have to have a very unique idea, right? And also another point is you need to um, intelligently put all the technology together in a different way. And I think that work, the giant robot work, definitely is belongs to this category, right? So let's move on. There are also some other recent work. They print liquid metal at room temperature, and let's see what it is. Okay, let me share it. Okay, so this technology allows the printing of those liquid metals in a room temperature. So so basically, this work is kind of invented by researchers in at NC State. So they utilize some alloy which is liquid in the room temperature, and they apply the heat source to kind of consolidate the droplet to each other. And it turns out some shape like this is developed. But although I think it's quite interesting work because, well, it saves the power a lot by doing this in a room temperature without those high power laser or electron beam and so on and so forth, which are used in other metal printing. But the material will be quite restricted. So only certain types of material can be used in this kind of process. So that's why I'm kind of still not too optimistic about this process. So if we could not find some real world application which need this process, then I don't know, maybe there could be some other applications coming out. But at this moment, I'm still quite still kind of not sure whether it will be a successful direction to pursue or not. Okay, so that's the thought on this work. Let's move on. Okay, the next technology is so-called 4D printing. So I would like to pause here, and you can have a 10 minutes break. And after the break, let's talk about the 4D printing in details. And I will show you some research work related to 4D printing in my group. All right? So see you guys in 10 minutes. Okay, let's continue our study here. So basically, another family of a new additive manufacturing process is the so-called 4D printing. So what is 4D printing? And let's check this video. Actually, this is a TED. This is a TED talk by one of the pioneer in 4D printing area. Let me open it.
This is me building a prototype for 6 hours straight. This is slave labor to my own project. This is what the DIY and maker movements really look like. And this is an analogy for today's construction and manufacturing worlds with brute force assembly techniques. And this is exactly why I started studying how to program physical materials to build themselves. But there is another world. Today, at the micro and nanoscales, there's an unprecedented revolution happening. And this is the ability to program physical and biological materials to change shape, change properties, and even compute outside of silicon-based matter. There's even a software called CAD Nano that allows us to design three-dimensional shapes like nanorobots or drug delivery systems and use DNA to self-assemble those functional structures. But if we look at the human scale, there's massive problems that aren't being addressed by those nanoscale technologies. If we look at construction and manufacturing, there's major inefficiencies, energy consumption, and excessive labor techniques. In infrastructure, let's just take one example, take piping. In water pipes, we have fixed capacity water pipes that have fixed flow rates, except for expensive pumps and valves. We bury them in the ground. If anything changes, the environment changes, the ground moves, or demand changes, we have to start from scratch and take them out and replace them. So I'd like to propose that we can combine those two worlds, that we can combine the world of the nanoscale, programmable, adaptive materials, and the built environment. And I don't mean automated machines. I don't just mean smart machines that replace humans, but I mean programmable materials that build themselves. And that's called self-assembly, which is a process by which disordered parts build an ordered structure through only local interaction. So what do we need if we want to do this at the human scale? We need a few simple ingredients. The first ingredient is materials and geometry, and that needs to be tightly coupled with the energy source. And you can use passive energy, so heat, shaking, pneumatics, gravity, magnetics. And then you need smartly designed interactions. And those interactions allow for error correction, and they allow the shapes to go from one state to another state. So now I'm going to show you a number of projects that we've built from one-dimensional, two-dimensional, three-dimensional, and even four-dimensional systems. So in one-dimensional systems, this is a project called the self-folding proteins. And the idea is that you take the three-dimensional structure of a protein. In this case, it's the Crambin protein. You take the backbone, so no cross-linking, no environmental interactions, and you break that down into a series of components. And then we embed elastic. And when I throw this up into the air and catch it, it has the full three-dimensional structure of the protein, all of the intricacies. And this gives us a tangible model of the three-dimensional protein and how it folds, and all of the intricacies of the geometry. So we can study this as a physical, intuitive model. And we're also translating that into two-dimensional systems. So flat sheets that can self-fold into three-dimensional structures. In 3 dimensions, we did a project last year at TED Global with Autodesk and Arthur Olson, where we looked at autonomous parts, so individual parts not pre-connected that can come together on their own. And we built 500 of these glass beakers. They had different molecular structures inside and different colors that could be mixed and matched, and we gave them away to all the TEDsters. And so these became intuitive models to understand how molecular self-assembly works at the human scale. This is the polio virus. You shake it hard and it breaks apart, and then you shake it randomly and it starts to error correct and build the structure on its own. And this is demonstrating that through random energy, we can build non-random shapes. We even demonstrated that we can do this at a much larger scale. Last year at TED Long Beach, we built an installation that builds installations. The idea was, could we self-assemble furniture-scale objects? So we built a large rotating chamber, and people would come up and spin the chamber faster or slower, adding energy to the system and getting an intuitive understanding of how self-assembly works and how could we use this as a macro-scale construction or manufacturing techniques for products. So remember I said 4D. So today, for the first time, we're unveiling a new project, which is a collaboration with Stratasys, and it's called 4D printing. The idea behind 4D printing is that you take multi-material 3D printing, so you can deposit multiple materials, and you add a new capability, which is transformation, that right off the bed, the parts can transform from one shape to another shape directly on their own. And this is like robotics without wires or motors. So you completely print this part and it can transform into something else. We also worked with Autodesk on a software they're developing called Project Cyborg. And this allows us to simulate this self-assembly behavior and try to optimize which parts are folding when. But most importantly, we can use this same software for the design of nanoscale self-assembly systems and human-scale self-assembly systems. These are parts being printed with multi-material properties. Here's a first demonstration, a single strand dipped in water that completely self-folds on its own into the letters MIT. I'm biased. This is another part, single strand dipped in a bigger tank that self-folds into a cube, three-dimensional structure on its own, so no human interaction. And we think this is the first time that a program and transformation has been embedded directly into the materials themselves. And it also might just be the manufacturing technique that allows us to produce more adaptive infrastructure in the future. So I know you're probably thinking, okay, that's cool, but how do we use any of this stuff for the built environment? So I've started a lab at MIT, and it's called the Self-Assembly Lab. And we're dedicated to trying to develop programmable materials for the built environment. And we think there's a few key sectors that have fairly near-term applications. One of those is in extreme environments. These are scenarios where it's difficult to build, our current construction techniques don't work. It's too large, it's too dangerous, it's expensive, too many parts. And space is a great example of that. We're trying to design new scenarios for space that have fully reconfigurable and self-assembly structures that can go from highly functional systems from one to another. Let's go back to infrastructure. In infrastructure, we're working with a company out of Boston called Geosyntec, and we're developing a new paradigm for piping. Imagine if water pipes could expand or contract to change capacity or change flow rate, or maybe even undulate like peristaltics to move the water themselves. So this isn't expensive pumps or valves. This is a completely programmable and adaptive pipe on its own. So I want to remind you today of the harsh realities of assembly in our world. This is complex things built with complex parts that come together in complex ways. So I would like to invite you, from whatever industry you're from, to join us in reinventing and reimagining the world, how things come together from the nanoscale to the human scale, so that we can go from a world like this to a world that's more like this. Thank you.
All right. Okay, so now you have some ideas about 4D printing, right? So in the 4D printing, there are some key words. First is self-assembly. So basically, so for the object, to be printed. So it will transform from one shape to another one, to one state to another state. And it is automatically done. So that is so-called self-assembly. And more specifically, in our case, so the shape will be 3D printed in one state. And then applying certain activation force. It could be heat. It could be some magnetic field. And the structure will be reconfigured into the expected shape. So that's the concept of 4D printing. And it is the 3D printing plus another D. So what is another, the other D? The other one actually is the time. So it's not just the shape, but also the time. By applying certain activation and wait for a little while, the object can be reconfigured into a totally new one. So that is the concept of 4D printing. So for example, like this one. So basically, this, let me just show you this website, and it make more sense to you. Okay, let me share the, yeah, let me share this website to you. So as you can see here, this is a box, right? It's a cube. But what actually people print is just this 2D pattern. And by applying certain activation, this planar shape will be folded to this cube automatically without any manual intervention. So that's so-called the 4D printing. And what they applied is just light. Okay, if you see this video, you will have some idea. Okay, so that is the some example of 4D printing, right? Oh, let me do the share right. Okay. So I would say most of the research right now is kind of okay. There are some options. Does it go back to its starting shape? No, I don't think so. It's a permanent deformation. But I mean, in general, it cannot go back to the original shape. But for some of those 4D printing process, they use the memory alloy, and if they do for the joint, right, for the hinge, in that case, it could go back to the original shape. But in most of the process, it's just a one-way process. And let me show you. Yeah. So why would you do it, other than because you can? Yeah, that's a good question. So actually, even in the TED presentation, the speaker didn't talk too much. But in my understanding, the possible scenario is for some of the scenario, like what he showed in the presentation, is like in the space exploration, right? So you have some part which cannot be transport and stored easily. So you can just dissect it to simple shapes, or in this case, two-dimensional shapes. And then when these are moved to like the outer space, something like that, and in that environment, you need this device to work. Then the self-assembly could be applied there, right? That's one consideration. Another benefit is actually I'm about to introduce in the next slides. Let me transfer to the other slide, and then you will have some more idea about this. So why 4D printing? Because we have some problems for current layer-wise additive manufacturing. It's slow and it requires support material. Also, as you can see, we mentioned several times the stair effect, right? So because of this a layer by layer nature of those current additive manufacturing process. And also it will generate the anisotropic material properties. It has stronger material property in XY direction, but worse material property in Z direction, right? So it's an isotropic material property. So what if instead of printing the 3D shape, we print only 2D sheets, and by applying the activation force, this 2D sheet could be automatically assembled to certain 3D shape, certain 3D object. Then it avoids the problems of this layer-based additive manufacturing, right? It reduces the fabrication and assembly time, and because we are just printing some 2D sheet, so probably you don't need support materials. And the material property could be improved if you print in 2D. That means there's no isotropic material properties. That's why people are thinking about to use the 4D printing to print the 2D shape and then apply some activation and wait a moment. And the 3D final shape could be obtained. Also, another possible benefit is the transportation, right? So you can just easily transport those 2D sheets instead of the 3D objects, right? So the 4D printing actually is closely related to another very ancient art, that is the origami. So as you can see, these very nice origami art piece are built from a piece of paper. And there are tons of methods and books and articles about how you're gonna fold a piece of paper to certain wonderful 3D shape. And also there are some complex patterns which give you some unique material properties by introducing certain unique patterns. So that actually inspired us to develop some self-folding structures for 4D printing. So you can see these are all existing 4D printing process. And most of them are from MIT, actually from the speaker, the one I showed you, right? His group. And they explore different materials and different activations but they didn't answer one question. That is, how about if I have a 3D design, right? If I know what I want, but is there any software or computational method tells us what will be the 2D patterns for the manufacturing? So they didn't answer this question, right? So that is the motivation of this work, basically to predict the 2D pattern for certain 3D targeting shape. So that's the motivation for this work. So we utilize those shrinkage film-based 4D printing process as our test, actually the experimental setup. So as you can see in this process, there are two different materials. One will be this a building material. Another one is another shrinkage material. So by applying the heat onto the two material, basically the shrinkage ratio of the two material are different. So that gives you this hinge-like motion, right? So it, like for example, if you have a pattern like this, and you could apply the heat onto this 2D pattern, and you will have all those banded shape. And the banding angle depends on the opening width. Basically, this is this L, the number of this L. And by doing so, you can control the angles for the banding. So that is the process. And so, for example, you could generate some patterns like this, and also this like a crane shape, right? So build upon this process. Actually, our work is the computational method to predict the 2D patterns. So the problem can be defined like this. So you have a 3D model represented by mesh surface. So what will be the 2D pattern which can be used in 4D printing? And this 2D pattern should satisfy that when it's self-folded back to the 3D, the folded shape is as similar as the given 3D model. So for example, if you have a certain shape like this, and this is your predicted 2D pattern, and after applying the 4D printing process, the folded shape should be as similar as the given shape. So that's the problem to be solved in this work. And we could model this transformation from 2D to 3D, from 3D to 2D as the so-called isometric mapping. And this isometric mapping satisfies this relationship. Basically, it measures the two corresponding edge on 3D and 2D. And ideally, in an isometric mapping, the length of two edges should be identical to each other. So that is so-called isometric mapping. But that is very difficult to achieve. So what we do is we transform this requirement of isometric mapping to a so-called rigid mapping. So what is a rigid mapping? Imagine you have a 3D triangle on 3D object, and you have a 2D triangle on the 2D pattern. If you could find a rigid transformation that is only having a rotation and a translation between the two triangles, if you could find this transformation, that means the two shapes can be rigidly transformed to each other, can be rigidly mapped to each other. So that is so-called rigid transformation. And we solve this by using a singular decomposition, a singular value decomposition method. And I might skip too many details. Yeah, for this, I just scale due to the time. But there are some problems by only applying this rigid transformation here. As you can see, this is the input model. This is the generated 2D pattern from the rigid transformation. But if we fold back this rigid transformed 2D pattern to 3D, you can see the shape is not approximated to the input 3D object well. So that suggests some improvements. We have to do something. So we introduced this cart. That means for the 2D pattern, we could have some carting on it such that the 2D pattern could be better approximate the 3D one when it falls back to the 3D shape. I don't want to go to the details due to the time limit, but just as let you know, we have two different parts, a boundary cart or interior cart. So the boundary cart will introduce a cart edge from one vertex on the 2D pattern to the nearest boundary of the 2D pattern. So that is the boundary cart. So the interior part, basically it introduces a cart, but it won't cut through to the boundary. So these are two different carts. So by introducing these two carts into this computation, we will have better results. Let me show you. So for example, without cart, you can only have a 3D shape like this, which is far from the input model. But by applying a cart here and here, you will have a much better shape like this, right? It compared to this one, is much better. But if you further introducing some boundary cart, you will have an even better shape after applying the activation to the 2D pattern, to the predicted 2D pattern. So similar case happens to this car model, right? And let me introduce the this process a little bit. Basically, it's a SLA-based process, and we just project different layers of the patterns using different materials, such that you could introduce the polymer materials with different shrinkage ratios. And it's a DLP process. And you can see here, basically it's a 2D sheet, right? And then when applying heat onto this 2D sheet, it will fold back to a 3D cube, right? So that's a typical concept. And here shows some testing result we have on how we build up these 3D shape using just 2D patterns. So basically, we develop a computational method for predicting the 2D patterns for 4D printing. So we introduce the rigid transformation into this computation. And also we introduce the cart insertion algorithm such that by introducing those carts, the generated 2D pattern can be self-folded back to 3D with better shape approximation, something like this, right? So that is the method to solve the design problem. What do I mean design problem? Because in a design problems, you have your target shape in your mind, right? You have your desired 3D shape, but you don't know how to design the 2D patterns to achieve this 3D shape. So that requires the computational power. And our work actually is expected to solve these design problems. And all right. So this is the, let me go back to this page and we can have a little discussion. So this is a computational method for the 4D printing. And yeah, we can have a little discussion on it, on 4D printing as well as the computational method here. You can share what you think about it. Any idea? So what do you think about? Yeah, I'm still struggling. So Kristen's point, I'm still struggling for a real world application. Seems like a good idea looking for an application. How do you keep it from folding when you don't want it to? So first of all, in many of an application immediately came to my mind is those aerospace applications. I don't know whether you know the news or not. So in the airspace applications like the satellite, they have those solar battery, right? They have a very big those plate for the solar batteries, right? So to launch the satellite to the space, you cannot have a very big space, right? For the rocket, but when the satellite is in the outer space, they have to span the solar battery, so that and make it very big area, and that requires this kind of capability. That is, you first fold it, and then you could deploy it into a 3D shape. So I would say that is the definitely most close application for utilizing this kind of technology. But another point here is, by doing the printing in this way, you actually avoid print the layers, right? And then you don't have the this kind of stair effect. So whether this could also help in some applications. I mean, to be honest, even myself, I don't find an exact scenario such that this kind of avoiding stair effect will help. But maybe that it could be a good direction to think about. Okay. So Clay's thing. How do you keep, oh, Doc's question. How do you keep it from folding when you don't want it to? Basically, all the folding is not automatic. I mean, it is automatically done, but you have to apply certain activation, right? For in this case, you have to put it into an oven to heat it up, apply certain thermal energy, then it will fold back. And in many other cases, it requires other source of activation, but still you need to put that activation. That means if you do not put the activation there, it will remain a 2D sheet. All right. Clay said like the iPhone. Okay. Okay. Doc said, but if it can be folded, it can be unfolded. Unintended force can happen anywhere. At my house, we call them children. Well, that's true. That's true. That's true. But imagine if, I mean, let's take the house as an example. If you can just self-fold, let's say you have a 2D pattern, which can be self-folded back to a 3D house, right? Yes, it can be reverted to a 2D pattern. But what if after it is self-folded back, after it is self-folded to the 3D house, you just put some like locker or somewhere such that it prevents this folding back, then it kind of solves the problems, right? Yeah, similar thing. for these real world problems, you had. I mean, I'm totally agreeing with you guys. For these real world applications, it's not just concept. You cannot just show some fancy example like this without consider about all these real problems, like what Doug suggested and Kristen suggested, right? So how you prevent it unfolded back, right? How you make sure this structurality is strong enough, right? Even in the video of the MIT people's work, they didn't consider this. I totally agree with you guys. It's still in the very early stage for this technology. But the concept here is to save material, to save the energy, to ease the effort of assembly, and in this 4D printing case, to eliminate the problems of stereo effect. What if we have this technology which print the object in a 2D manner and then applying certain activation, and then it will deploy to a 3D object? So will this be meaningful or useful for some application, for certain application? Actually, that is an open question. And what we did in this work is kind of trying to think about this problem in a design perspective. That is, imagine you have this technology available, and it has some application. But how are you going to utilize this technology for a design and manufacturing? That is, you have a target 3D shape. What are you going to manufacture in 2D such that the 2D one can fold back to a 3D shape, which is exact what you want? So I can only kind of explain the work in this way, and I totally agree, and I kind of admit it's still far from an application, far from a real world application, and there are a lot of engineering problems need to be need to be thought about, especially in terms of the reliability, in terms of the structurality, and so on and so forth, and also the environment, even for the for the outer space exploration for the NASA. you have a very extreme environment, and there are a lot of uncertainty, and each of these uncertainty could crush the whole thing, right? I can imagine how difficult it is, but well, this process has so many, well, I would say possibility, and that's why people are looking at it and see whether you could find something, you could gain something by doing this in this way. And I would say it's a quite kind of, it's not, I mean, if we divide research to some application research, some like advanced research, or some even more advanced research, this is a more advanced research. It's far from application. It's not that there yet, I would say. Okay, I would like to hear from you. Any other points want to share? Yeah, I mean, actually, this kind of technology, they came out for a while, for a few years, but till now I didn't see any real application. Yeah, I mean, sadly, I didn't see any application yet. Okay, if there's no other thoughts on this. I think it's the end of this class. And in next class, which I will post it online in a form of video, I will kind of talk about some future directions for additive manufacturing, and also definitely I will talk about some of my thoughts on additive manufacturing. What will be the most important thing in next few few years, like 5-10 years, and what could be the issues, something like that. And well, let's talk more in the future lectures. And oh, again, Kristen, Tommy, and Scott, please submit me your presentation done on Tuesday. Right, I will keep a record to mark your project. All right, send me through email. Okay. Okay. Thank you guys, and yeah, keep in touch. You can, any questions, any thoughts, just let me know. All right.
Okay. Thank you.
Okay. Bye, guys.